Welcome to my house. Welcome to the Structure Talk podcast, a production of Structure Tech Home Inspections. My name is Ruben Saltzman. I'm your host, alongside building science geek Tessa Murray. We help home inspectors up their game through education, and we help homeowners to be better stewards of their houses. We've been keeping it real on this podcast since 2019, and we are also the #1 home inspection podcast in the world, according to my mom. Welcome back, Tessa. Great to see you. And Tom, we've got Tom Harris on the show again. Three-peat. I think you might be the first podcast guest we've ever had to do 3 episodes in a row just to cover all the content. We got so many questions, and you've got so many fantastic answers to all of this. So we got you coming on again. Maybe just a reset for anybody who missed the first 2 episodes. Go back and listen. There we go. No, just kidding. No, just kidding. Tom, he got a little funny when I said this last time. I said Tom's a spray foam expert, and I don't know if Tom liked that term. Tom knows a ton about spray foam insulation, and he's been working as a consultant for spray foam, and he's been in this field for the last, 25 years now, Tom?
Thank you, Ruben. I appreciate that. It's 43.
Oh my gosh. So you were with BASF for 20 alone, right?
Yeah.
That's what I was thinking.
Canada and the U.S.
Oh my goodness. Yeah.
Yeah, it's been quite an adventure, you know. I mean, and I'm still learning every day.
Yeah. Oh, well, we're so glad to be able to pick your brain, and I feel like we're just going to kind of pick up right where we left off on the last episode. And I felt like I was hogging a lot of the questions. I wanted to give Tessa a chance to get a few of her questions in here.
Well, the last couple episodes were really fun, and I've learned a lot from you, Tom. But one question I have personally is I'm curious about what you think about hot roofs. And first of all, let's just define what a hot roof is for anyone that's listening that doesn't know. So that's when you move that thermal boundary and pressure boundary up to the roof deck. So maybe you've got an attic space that has a furnace or ductwork in it. One way to try and bring that ductwork into the conditioned space is to move that thermal boundary up to the underside of the roof deck. So now that attic space is technically conditioned. So there's different, applications where you might do a hot roof, like like I just mentioned with a retrofit, if there's a furnace up in the attic or air handler or something like that, or maybe even you've got vaulted or cathedral ceilings. Maybe, the insulation is moved up to the underside of the roof deck in that situation. So I've seen my fair share of hot roofs here in a very cold climate in Minnesota. And as you know, moisture can be a real problem. Interior moisture, humidity levels can be an issue. If you've got, little gaps in that thermal boundary or pressure boundary, just warm, humid air from the interior can leak through and then get trapped on the underside of the roof decking, condense, and create all sorts of moisture issues. You can rot out your roof decking. You can create frost that can lead to, water dripping back in, all sorts of things. And so it's really important that it's done properly, correctly. But there's just so much I don't know about it. And from, talking to you, Tom, you get to see these things all day, every day. And you've, been in this consulting world for a long time, and the chemistry of spray foam and how it should be installed and what products to use. So I'm just wondering if you can kind of share with us, how it should be done, what type of spray foam to use, depending on your climate or your region that you're in, how much should be added. And then, also if you've seen any issues with it too, or kind of what's the up-to-date industry kind of knowledge around hot roofs these days. So it's not a very direct question, but I'm just ready to dive into this topic and hear anything you have to say about it.
It's your standard 9-part question.
I appreciate that.
Anywhere you want, Tom.
I feel like the president in an interview. But Yeah, hot roofs are becoming quite common, and they're now codified in the most recent codes. They're identified, moving that thermal boundary from the floor of the attic to the underside of the roof deck, especially in the south where this concept started, is great when you want to enclose the mechanicals. You now move the mechanicals into a controlled atmosphere, a conditioned space. They last longer. They work easier, more efficiently, this sort of thing. And that's really where it started, with the concept of enclosing the roof attic for the mechanicals. Great, good idea. Now we start to move north, and we don't see as much mechanicals in the attic space up here. It's mostly in the conditioned space as it was designed when the building was built. That thermal boundary ended at the attic floor or top floor ceiling, and we lose that attic space. It becomes uninhabitable, unusable. You don't want to store things up there. So the thought was, hey, I can get more square footage in my occupied space. I can maybe put a bonus room up there, or man cave, whatever you want to call it, but I can use that space maybe for storage. And we've started to see the migration of hot roofs, unvented attic assemblies, technical term for it, in the north. Okay, well, that's great. It's a super application for foam, and it makes sense. Now, getting it right is, as you've identified, twofold. We need to make sure that the thermal envelope that's coming down the roof deck in an unvented attic assembly, that means we no longer have venting. Those ridge vents go away. The soffit vents go away. There's blocking that actually terminates and defines the attic space from the soffit box. That's now insulated and thermally isolated. And that's important because in the code, we're allowed to downgrade the thickness of insulation, the R value that we install, so long as we apply the foam down the roof line and get to the cold side in the north, the exterior side of that wall plate. Because when you're in the attic, you can look down, you can see that top of the wall plate. It's sitting right there. So when we block the soffit with various blocking materials, I like isocyanurate or extruded polystyrene board stock for that purpose, but we block it off and then we spray foam to it. So long as our blocking is on the outside edge and allows the spray foam to totally encapsulate that top plate, and we bring it into the attic onto the floor by about 6 inches. And that gives us that full coverage and doesn't create a cold spot along our top plate of our wall. Now, choosing between open cell and closed cell, that's the two options we have in spray foam. In the north, we go by the building code, and it says in climate zones 4A and above, that's 5, 6, 7, and 8, and we're in 6, 7, some parts 5, but we're in the colder climates here. We need to protect what they call permeable insulation, and that's open cell foam. If it's vapor permeable, which means it has a perm rating, ASTM E96, of greater than 1, that's vapor permeable insulation, and you need to protect that with a type 2 vapor retarder. And that's something that it has a perm rating less than 1. So there's a recognition of, as you spoke earlier, Tessa, about condensation and moisture control in primarily heating climates like we're in. That relative humidity can potentially build up in the attic because moisture in air, warm air rises, this sort of thing, and it gets to the attic space. All right, so now we have relatively warm. It's in an insulated space, and it's containing moisture. And in the cold climates like we're in, it wants to drive, what they call the vapor drive, is from inside to out. And if it carries moisture through a permeable insulation, like open cell foam, It goes through the insulation and has the potential to condense on the underside of the roof deck. Right? This makes sense. Cold surface condensation create all that sort of stuff. Yeah. So the thought of the building code and most building practitioners will say, well, look, protect it with a vapor barrier or a vapor retarder. And they define in the code what level. And we need a class 2 or type 2 vapor retarder. That's great. So when the job is done and then the contractor's gone away and we look in our nice pretty attic now, we should see in open cell applications a paint, if you will. And that's a vapor retarding paint, various levels that you can buy. That protects the foam from this moisture and moisture in the air, the relative humidity that's building up in the attic space. That's moisture control. So in our climate zone in the north, 4A and above, you need to protect permeable, vapor permeable insulation with a type 2 minimum vapor retarder. So if we go up in our attic and we see that there's no white paint or anything like that on our foam, especially if it's open cell, that gives us cause for concern, questions at least. The other option is to use closed cell. Well, closed cell in and of itself is a less than 1 perm insulation material. So it's not vapor permeable. So it does not need an additional vapor retarder. It can be bare foam. Now, that's vapor and moisture control. The other issue that I want to draw attention to, especially in retrofit applications where the attic may be used for storage or maybe even a conditioned space for a bonus room or a man cave, these sorts of things. It is now classified as occupied space, living space. And that means the foam, which is always considered combustible by code, that needs to be protected with a thermal barrier, and that's typically drywall. There are other options. If you're not planning on bringing the neighbors up to the attic and enjoying a football game, it's not a finished space, you may choose to leave the foam exposed in your attic. That foam must be, at all times, protected from fire propagation with a 15-minute thermal barrier, typically drywall, or some other fluid-applied thermal barrier that has got all the approvals. And in our industry, 99% of the foams that we use, both open and closed cell, have a litany of testing for fire protection. So there's a number of options for this paintable thermal barrier. Drywall is accepted, and there's other building materials that are actually stated in the code that you can nail on to the framing members. So that's the reasons why and the getting it done. Now, there are some concerns that you've probably heard, things like voiding shingle warranties.
Manufacturer's warranties.
Yes.
Mm-hmm.
Yeah, that is a concern. And the thought there from the shingle manufacturers is, hey, if I pound insulation up underneath my sheeting and I've got shingles in direct contact with the other side of the sheeting and they're in the sunlight, they heat up, they can't dissipate the heat to the inside of the attic. Nobody wants to live in a hot space, so we insulate it. And the thought process at the shingle manufacturers was, if you insulate that, I lose my ability to radiate and dissipate the heat load into the attic space. That's not good. You're going to prematurely fail my shingles, and I'm going to therefore void the warranty. So it's always recommended before we do hot roofs to make sure that the warranty of the shingle manufacturer is always looked at to see if we're voiding that warranty. Now, warranties and websites are ever changing. So refer to that specific manufacturer's warranty documents, within a month or two of the installation date, just to make sure. There's a lot of research that's gone into that actual claim that we're prematurely failing, and what is the temperature impact on shingles. And, if you insulate the underside of roof deck, we're somewhere between 5 and 8 degree increase on shingles. Now, you can affect that shingle temperature more by changing the color of the shingle than you can by adding insulation to the underside of the roof deck. And that's an important point. It's interesting that a lot of the manufacturers, although not stating it on their website, if you ask them for a letter talking about vented versus unvented attic assemblies, you'll come to find that most manufacturers now allow unvented attic assemblies. So times they are a-changing, Dylan used to say.
Okay, so just as a quick recap to make sure I understand, you'd say that definitely probably closed cell spray foam would be a better choice in a cold climate region to use, just because it probably already has the built-in vapor barrier to it. You don't need to apply some sort of paint that will be a class 2 vapor retarder.
That's correct.
And you get a higher R value per inch too. So it's kind of a win-win for a cold climate situation. Would you agree with that?
That's what we're seeing. Yeah, the market dictates. Okay. I mean, open cell foam, it tends to be a little less expensive, but you've got the added cost of trimming and that sort of thing, and the need for this additional step in a vapor retarder. But you're always going to put that step there, at least I hope, because you're going to spray something onto the surface of foam, whether it's open cell or closed cell. You still have to address the fire issue.
Can you have a class 2 vapor retarder that doubles as when I was working for a spray foam company, we called it an ignition barrier. I don't know if the terminology has changed, but can you have a product that does both the vapor retarder and the ignition barrier or thermal barrier?
That's a great question, Tessa, and it is a bit confusing, I must say. Fire protection is in actually 3 categories or 3 approval processes, and it all depends on how you're going to use the attic. And the building code it's not left to guess. The building code is quite specific on what level of protection is required for the occupancy use and the access and the distribution of the air and all these sorts of things. They're all laid out in the building code, but there's sort of 3 levels. One is a thermal barrier, and there are fluid applied thermal barriers, these sprayed on products directly onto the foam, or there's things like drywall. That's a thermal barrier. There's also ignition barriers. Now, you can protect foam with an ignition barrier so long as you meet certain storage occupancy use, categories and requirements to allow you to downgrade from a thermal barrier to an ignition barrier. Okay. Now, there's a third category that says, hey, you don't need any thermal barrier or ignition barrier because you're barely using the attic. And
this is not finished space, not usable.
All this sort of thing. That's right. Yeah. And it's laid out in the building code. But in some instances, and they're quite narrow, these occupancy loads are quite restrictive when you use unprotected foam because it's combustible. And we want to give people the ability to evacuate a house if it's on fire. And the rule of thumb is we give them 15 minutes. So it's a 15-minute thermal barrier, a 15-minute ignition barrier, or it's unprotected foam. And that test criteria is quite specific, and the occupancy is quite narrowly focused. You can't do too much. And the problem I have, and one of the concerns I see, is if we install it, let's say with an ignition barrier on day 1, we sell the house and somebody else decides they want to use the attic and they think they've got fire protection. They may not. So we're changing the occupancy of the attic space and not living up to the requirements of that change if we don't confirm that our foam is protected with a 15-minute thermal barrier. So that's a good topic, and it's a good thing to understand.
So can you get a product that does both the vapor barrier then and a potential ignition barrier? Because that sheetrock would be like an example of a 15-minute thermal barrier. It sounds like the most protective.
Right.
But if you're just going with a ignition barrier, you're not finishing the space. Can you get a fluid applied material that does both the vapor retarding and the ignition?
Yeah, good question. And up until I would say July, August of last year, the answer was no. You need two products. You need a vapor barrier, spray applied vapor barrier, and a thermal ignition barrier sprayed over top of that. So now it gets really expensive. And lo and behold, one of the ignition thermal barrier manufacturers by the name of No Burn, they've come up with a product called Spray Seal that actually is a ignition barrier, thermal barrier, and type 2 vapor retarder all in one product.
Okay.
Yeah, and that's new to the industry. So that's very, very recent stuff, and it's very cool. It will allow open cell to be used north of climate zone 4A. It's so long as they install this product that's thermal barrier, ignition barrier, and vapor retarder all in one.
So now, as a home inspector, if I'm coming in and I see that, if I see it, what is it going to look like? I mean, is it just going to look like it was painted white?
Yeah, it looks like whitewash paint on your fence or acrylic white wall paint and painted onto foam.
And if I'm going to know the difference between a thermal barrier or an ignition barrier or a vapor retarder or both, I'm going to have to ask for the product. There's nothing I can do to look at it and say, it's this.
And
right?
that's the conundrum of inspection. It gets down to mill thickness, the actual thickness of the paint when it's installed. That dictates what protection level you have.
How about if I just took a blowtorch to it?
No, don't take a blow. No.
Okay. All right. Fair.
You're one of those guys. Yeah.
Oh, very much so.
Yeah. Don't do that.
Yes.
Okay. All right.
Yeah.
No, I say that tongue in cheek. I kid.
What you'll see when you get up into the attic, foam has a pretty distinctive natural color. It's kind of an off yellow, a lot like sand. That color. And when you paint it with an ignition thermal barrier, some of these you can pigment black or blue or whatever you want to get, but most are white. So it'll look like white house paint has been painted over the foam. And that's a good thing. If you want to do a physical test, you could put your thumb on it and push a little bit, and that top painted layer will snap. Now, I'm not saying to conduct a destructive test just to see. You can probably do it visually.
Okay. All right.
So I have a quick question. Going back to the open cell foam. So if you're in a hot, humid climate, typically, are they still applying vapor barriers to the exterior? And if so, if you've got a hot roof situation, you wouldn't want to put a vapor barrier on the inside of that foam, right?
Yeah, that's interesting. Good question. Good pickup, building science, Tessa. I've actually ran condensation models for a number of contractors that have asked exactly the same question. And you're right. We don't want to put a vapor barrier. Now, there's a difference between a vapor retarder and a vapor barrier. You don't want to put a vapor barrier on the inside of open cell foam in a hot, humid climate. You want that material, if it does happen to pick up moisture, you want it to breathe or dry in both directions, out and in.
Yeah.
Primarily, the vapor drive is from outside to the inside because we condition that about, I like it about 65, but that'll cost me a lot of money. But, 68, 70 degrees in Florida, that's pretty acceptable. but the outside temperature is 95, 105 with, in Florida, a lot of relative humidity. And the vapor drive is from outside in. So they look at it the other way around and they say we need vapor, moisture control layers from the outside of the insulation material. Gets tricky in climate zone 4 and 5. What do we do there?
Right.
But in the extremes, up in Minneapolis, where we are, and down in Florida, it's very manageable. It's just a different approach to building science.
Okay. I see Ruben, I see your face. You've got a question. Go ahead. I'll come back to mine.
Well, two of them, but I don't want to interrupt your flow. But I wrote them down. I'll remember to get to them at some point.
Okay, so what do you do in climate zone 4 or 5 then? Sorry, Tom, I'm going right to the heart of the problem. Okay, so when you need drying, when you've got moisture coming from both the inside pushing out and outside pushing in these mixed kind of climate zones or humid climate zones, what kind of foam would you recommend? And do they need a vapor retarder? And if so, what side?
The building code dictates, and there's a lot of websites out there that'll tell you what climate zone you're in if you just put into Google your address, climate zone of whatever. And if we take something in the middle of the country, it'll tell us which climate zone we're in, which will therefore tell us where to put the vapor barrier, the vapor retarder, and to what level of insulation we need. Don't forget that moisture control and condensation in our wall and roof assemblies is really the purpose we insulate. We want to control that condensation plane. It's not all about energy. It's a lot about condensation and moisture control so we don't rot our buildings out. So in the middle of the country, we have what some would say an excessive requirement for insulation. And that's to control that condensation plane so that if condensation occurs, we can dry in both directions. The middle of the country has, let's call it a moderate climate for now, but its construction techniques, as dictated by the code, allow for drying in both directions. And you can see a lot of assemblies, the way we build in the middle of the country, it's different than the way we build in Florida, it's different than we build in Minneapolis. Those assemblies, wall and roof, can dry in both directions. We control the condensation plane or the dew point within the insulation by the amount of insulation we install. And again, that's dictated by the code.
Okay. Thank you.
Okay. I'm not saying that an R60 roof in Maine or Vermont is a must-have, but it's all about condensation control, and those R values are high for a reason. Our more common insulation materials don't really. There's an old term that I shouldn't be using, but I will, called effective R value. When we measure the R value of our insulation materials in accordance with FTC, Federal Trade Commission, which says we're protecting consumers and they can't buy something that they don't know. So let's have an insulation test. And that test only defines one aspect of heat transfer, not air infiltration. And the DOE says that 40 to 60% of our cost of HVAC with any building is associated or due to uncontrolled air leakage. So it sounds to me like uncontrolled air leakage is a pretty big issue. And if we look at fibrous, cellulose, some of the other not spray foam materials, and I'm not knocking them. They have their place for sure, but they do have some limitations and capabilities to actually insulate. So if we're talking about fiberglass, it gets wet, but it dries quickly. That's a good thing. The issue becomes I can transport air through it. And if
Mhm.
I'm building a fat wall at R60, I've got to put some sort of air control layer in there because I get convective looping in fiberglass bats, and
Mhm.
it degrades the thermal efficiency of the bat. And I think these energy codes, R60s and whatnot, are kind of thinking about, the more air permeable, the more vapor permeable insulation materials, and making sure we've got enough thickness of those. Now, when we turn to spray foam, it's a different conversation. Spray foam is an air barrier at, about 1.5 inches, which is like R10. So you're not ever going to see that anywhere. We see, 3, 4, 5 inches of closed cell foam that has an R value of 7 per inch. But it does more than the conductive ASTM C518 FTC test thing says. They say it's R7. Does it perform like R7 when you get it into the application, into the field? Well, we know fiberglass does not maintain its R value in performance. We know cellulose has a downgrade. Strangely enough, spray foam outperforms its stated R value by adding these concepts of air barrier, moisture control. It doesn't get wet. So there isn't periods where, hey, my insulation's wet. Now I've got no insulation at all. Closed cell foam doesn't get wet. And if you properly protect open cell foam, it doesn't get wet either. And it is an air barrier when it's 3.5 inches thick. So, there's the code and building science have got some challenges between themselves, some disagreements per se. I struggle in the spray foam industry because we, from time to time, may overstate the performance of spray foam, either open or closed. But the majority of times, we're getting it right because we're abiding by code. And if it says R60, well, it's R60. It's going to be expensive, but it's R60. And it will perform like R60. If you have R60 of a not in kind type of insulation, it may not perform like an R60. So in the insulation industry, it's a very robust conversation about R value.
Sure. Well, Tom, I wanted to come back on a couple of things when we were talking about ignition barriers and fire barriers. Correct me if I'm wrong, but one of those exceptions in the code where you can always leave it exposed is at the rim space, right? Like nothing needs to be done there.
That's correct. And that's stated in the code.
Okay. All right.
As long as it isn't more than 3.5 inches thick.
Okay. So we can leave the rim space alone. That's okay because we just consider it such a small belt going around the house. We don't need to get whipped up about that. You're
familiar with the thermal bypass report from the Department of Energy? The rim joist. The rim joist is actually in the top 3 of air leakage points in any house.
Sure.
I've replaced my windows in my front room, and I've got a couch up against the front window. That's great. My dogs use it for where they need to sit, but I can sit on that couch. I got new windows. I can still feel a draft. It still feels cold about 3 inches down from the face on my drywall, about 3 inches down from the window. Why? It's coming up through the baseboard, the rim joist, because mine aren't insulated. It's coming up through the rim joist, getting up into the wall cavity and coming out. And I can feel it. So yeah, that rim joist spot, that's a beauty.
And I'll just share anecdotally on that same vein. My last house was built in 98. And one of the first things I did after moving in and it had an unfinished walkout basement. First thing I did was have a contractor pull out all of the fiberglass insulation because you could see mold growing on the poly that was covering all of it. We pulled all of that out and then spray foamed all the walls and spray foamed the rim joist all the way around the basement, and it was fantastic. Made a huge difference. And now I'm in a house that was built in 2001, a little newer, but has a fully finished basement, and the rim space is insulated with fiberglass bats. And there is a dramatic difference in the two houses when I'm standing near the outside walls. At my last house, it was just comfortable. The floors are fine. But at my newer house, I feel a big difference in the winter. When I'm standing right next to the outside walls, my floor is much colder. And I miss that part of being in my old house.
Yeah, and that's an inspectable rim. That is an inspectable, especially in the mechanical rooms. They're usually not finished. So you can go in there and you can have a look at that rim joist. And home inspectors, on my report, I have rim joists uninsulated, and that was disappointing when I bought the house. I have a finished basement now. I have no access to the rim joists, but boy, I wish it was insulated with spray foam. There's a great term to see on rim joists: insulated with spray foam.
Yes,
beautiful.
Yep. And then one other thing I wanted to ask you about when we're talking about ignition barriers. I mean, I know we're talking more about spray foam, but you know about all types of foam. So I got to ask you this one. I've run across this on a couple of houses where it's new construction and the builder has insulated the basement foundation walls with blue boards. I don't know what is that stuff. Polyisoanurate?
Blue board?
Yeah, the big blue 4x8 sheets.
Yeah, and it's blue?
Yeah.
That's extruded polystyrene.
Okay, it's extruded polystyrene. So they use that, and there's nothing over it. There's no paint, drywall, nothing. Is that okay?
Personally, no. But code-wise, you're allowed to do it in some jurisdictions.
In some jurisdictions.
There's a difference between the basic chemistry of polystyrene and polyurethane. Polyurethane, spray foam, is what they call a thermal set material, which means if you put a blowtorch on it in a fire, it creates a layer of char. And that char actually protects the foam and all that sort of good stuff. A thermoplastic material, when it sees heat, it melts. And if it's hot enough, those drips can become what they call flaming embers. And that's not good. The Grenwall fire and all this sort of thing, there's many examples where polystyrene based products have not performed well under a fire load. Polyurethane is a thermal set and it reacts to fire completely differently.
Okay.
If that's such a term.
Okay. All right.
Yeah.
Well, that's helpful.
They're plastics. They're combustible insulations. They have a flame spread, and extruded polystyrene has flame spreads less than 25. I don't know the particular brand or what it is you've got there, but I would assume it has a flame spread under a standard test, which does not reflect actual fire conditions, but it's a test that we use in the industry. And it's probably got a flame spread of less than 25, which is pretty good. Wood has a flame spread of 100. Drywall has a flame spread of 0. And these plastic insulations have flame spreads of less than 25. So is it going to suddenly propagate flame and pose a problem? No. But I would protect it primarily from the smoke issue and from damage with something. And it is a plastic, it is combustible, so I am not personally comfortable with leaving it exposed, but it is depending on the code. Now remember, Ruben, that the codes, there's the International Building Code, International Residential Code, and the International Energy Conservation Code, IECC. right? Those 3 codes. They're not real. They're what they call model codes. Each state can adopt whichever model code version, year, essentially, and they're reprinted every 3 years or reworked every 3 years. And a state has the authority to implement whichever code version it wants. That's one way it could change. The other one is a locality, a community, a county, which has its own set of codes. They could change it again.
Mm-hmm.
They could adopt whatever they want. So you see that it may be a model code requirement, a state code requirement, but not a local code requirement.
Gotcha.
Yeah. So, in order of priority, the code that matters is the local code. And that's why local code officials are so important in the whole conversation.
Sure. Okay. Very helpful. Thank you. Well, next time I see the blue stuff, I won't get whipped up about it, but
well, now you know a little bit more about it.
Yeah.
Don't put a torch on it.
Yeah, don't put a torch on it. I'll try to remember that. All right.
Well, and in parts of the country that have crawl spaces and they're insulating the perimeter with like a rigid foam or spray foam, and just depending on their code, it's likely that they'll need to have some sort of like thermal barrier or ignition barrier applied over that, right?
Well, the code treats, and I don't want to use the term confined space, but these unoccupied areas or partially occupied, maybe for service of mechanicals.
Yeah.
In crawl spaces and attics, it treats crawl spaces and attics the same, from a use of insulation, spray foam, protection, thermal barrier, ignition barrier, all that sort of thing. Code says that an attic is the same as a crawl space, and a crawl space is the same as an attic. Where we run into problems is groundwater, ground moisture, termites, and a homeowner and a builder that wants to do the right thing in accordance with the energy code. You want to insulate up underneath your crawl space. There are ways to do that correctly, and there's ways to not do it correctly. And again, like an attic, you have vented and unvented.
Mm-hmm.
So the same circumstances exist: an unvented crawl space or a vented crawl space. And depending on if it's vented or unvented, that will dictate where you put the insulation. So imagine a house up on piers. You've seen these beach houses with 5 or 6 cement blocks, and then there's a house on top of it.
Mm-hmm.
They want to insulate the underside direct to the underside of the floor.
Mm-hmm.
Mm-hmm.
And you want to protect that insulation from high humidity. I mean, in Louisiana, we build on the bayou. I mean, it's over water.
Mm-hmm.
That's a high humidity condition. And if we're running a air-conditioned space above the floor, the vapor drive is severe and constant. So I want to put a vapor barrier on the warm side of the insulation, which means I would spray my foam in place and then spray a vapor barrier over top of that.
Mm-hmm.
Call it an insulated, vented crawl space.
Mm-hmm. Yeah. Thanks for highlighting the differences in how crawl spaces can be treated and addressed, because there is such a mix out there of vented or unvented. And then depending on all of that, like you said, where that thermal boundary should go varies greatly. So it's helpful just to hear it from a spray foam expert where we should be seeing it if it's a vented crawl space right up underneath the floor.
If it's vented, yes. If it's unvented, then we spray the walls.
The perimeter. Mm-hmm.
Yeah. And some people spray the floor. For example, in Canada, most of the houses now, they actually spray foam onto the gravel before they pour the floor for the basement.
They're not using rigid insulation foam boards, they're using spray foam?
Yes, because it's
Huh.
monolithic, all one
Oh,
piece.
yeah.
Doesn't
Wow.
crack, no gaps, because you're protecting against a gas, radon
And
gas.
radon too, yeah.
Yeah, that's the
Interesting.
key. So we get a double bonus there when we address radon, either with board stock or spray foam. Now you've got an insulated slab. Why don't we put some sort of heat unit into our slab, and now we've got a heated floor.
That's the
Mhm.
best.
Yeah, it's cool.
Ruben's a
That's
fan.
cool.
Huge fan.
That's the spin-off advantage of trying to address radon with insulation. Now we've got an insulated slab. And insulated slabs, by the way, don't crack as much because you've
Less
isolated
expansion
it.
contraction because they're
Yeah,
in kind of this similar temperature year round. Yeah.
exactly. And that's why I
Yeah.
prefer to have insulation on the exterior of foundation.
Yes. Don't
You know,
we
it's
all?
the
Yeah.
Swedish fireplace mass, thermal mass kind of stuff. But
Yeah.
you eliminate cracking because it's not seeing a delta T,
Yeah.
and it stays warm because you only warm it up once.
So
It's not subject to the outside environment.
Yeah.
speaking of foundations and exterior foam, one last question for you, Tom, and then we should probably wrap this up. But what do you
Ah,
think about putting closed cell foam directly to the interior of a foundation wall that's, it doesn't have any sort of waterproofing or damp proofing on the exterior of it, so it's taking on moisture constantly, but now it can't dry to the inside. Are there any potential issues with that structurally?
I've seen it done lots of times and without problems. I
Okay.
prefer putting it on the outside, but if you do want to put it on the inside, if you're in flood zones, there's ways to actually have that foam be exposed to gray and brown water for for a short duration. When the flood waters recede, you can actually put a blower in the bottom, as long as your drywall's up an inch, cover it with a baseboard, that sort of thing. Take the baseboard off and you can blow dry it. You can't do that with fiberglass or other non-closed cell materials. As a matter of fact, closed cell foams are approved for use in flood zones by FEMA. And they're the only products that are, for that very reason, because they don't accept a lot of bulk water. Now, in foundations, to answer your question more directly, if I've got spray foam on the inside of a foundation, and let's assume that it's fully cured and dry and all that good stuff, would you damp proof the outside? I would. I'm not going to get a lot of vapor drive from inside to out, and I'm going to control where it condenses, even if it does get through it, through my thickness of insulation. And I'm going to make sure it's not going to condense anywhere in the CMU. How do I protect the CMU from exterior bulk water if we're below the water table and it's going to get hydrostatic pressure of water and it's going to need to be protected? So I would use robust damp proofing.
What if you're dealing with a retrofit situation, though? A house that's, let's say built in the 1950s, CMU block, no waterproofing or damp proofing on the exterior, and someone wants to insulate their basement and finish it. They put closed cell spray foam directly in contact with the concrete block on the inside, but there's no sort of damp proofing or waterproofing on the exterior. Is there a risk there with, trapping moisture in the block and creating issues structurally?
Yeah, and you're exactly right, Tessa. And your questioning is perfect. You said in a questioning manner, is there a risk? To me, as a building science guy, there's got to be an answer for that. There's got to be an equation somewhere. There's got to be a model that I can run to say yes or no. Is there a generic rule? Not really. But there are modeling programs that you can, buy inexpensively and test that theory to run those models. And that's what I would always suggest people that have questions, seek the answer through science first, not necessarily through social media.
Or if you're Ruben, you just do it and then you find out later.
Well,
That works
yeah,
too. We need people on both ends of the spectrum.
well, that's what experience teaches us. I mean, I don't want to pick on Ruben. I'm sorry, Ruben, but if you make a mistake, I'm going to get the call, and I'm going to get to learn something. So that's kind of a good thing.
Yeah, yeah.
I don't mind that.
I've made way more mistakes than a lot of other people because a lot of the time I just need to try it myself and deal with the consequences.
We all appreciate that, Ruben.
If I could provide a kind of a plug for somebody, there is a building science practitioner out there by the name of Joe Stebrick, who has a website and a company, Building Science Corp. And if you Google Building Science Corp, it'll take you to Joe's website and his company's website. And it is absolutely chock full of all kinds of reports and data, and it's just a wonderful resource for people to read. It's searchable when you get there. You can put in some topics, things you like hot roofs and unvented attic assemblies and crawl spaces, all this kind of stuff. And he does a wonderful job of explaining the building science behind what could happen. So if people are looking for more reading rather than gaining experience through mistakes, go to Joe's website and check out Building Science Corp.
Tessa and I are huge fans. Absolutely.
Yeah, that's a great recommendation. Yeah, thanks for saying that.
Yeah.
Perfect. Well, Tom, thank you so much for coming on our podcast. And we've asked you questions now for three straight hours. So thank you for taking the time. Really appreciate it.
Oh, it's a pleasure. If anybody is listening that's in my industry, I have the reputation. I could talk on foam for many, many hours. So no worries at all.
All right. Well, Tom, thanks again so much. And I'm sure we'll probably have you on the show again. Next time Tessa and I have enough questions piled up, we'll have to get you on again, but we'll definitely stay in touch. And as we did in the other episodes, we'll be sure to put a link where people can get in contact with you in the show notes. Can you just throw out your website one more time for us?
Sure. It's www.letstalkpur, short form for polyurethane. So it's letstalkpur.com.
Excellent. Tom, can't thank you enough. Appreciate all of your time. Thank you so much for coming on. And if you got any questions for Tom for future episodes, feel free to email us. It's podcast@structuretech.com. I'm Ruben Saltzman for Tessa Murray, signing off. Thanks, everyone. Take care.